Hello everyone. In this video I'm going to give you a tutorial solution on inference lines for statically determinate beams. So in this example here, you are asked to draw the inference lines for A, the vertical reaction at B, and then B, the moment at C, okay, and then question C is the shear at section C, okay, also at this point here. And then we assume B and D here, they are rollers, okay, where support A is a pin. So let's just solve the first question, which is to draw the inference line for the vertical reaction at B. Alright, so now we are going to use the method of qualitative inference line to draw the shape first. Okay, so the shape of the inference line for reaction at B. Okay, so originally we have a beam like this, okay, and a pin here and a support there. Okay, and then this is B, right? And then this is a pin support, and then this is a roller support here. So now we replace the support at B here with a roller guard, okay, which we can push the beam, okay. So we push the beam with By, okay, and then this is a natural hinge here. So if we apply a force here and push the structure here, okay, then the structure will deflect like this. So this is the hinge here, okay, there's the natural hinge, and then that is the deflected shape of the beam if we apply By. Okay, so this is the qualitative method in determining the shape of the inference line. Alright, so now we know the general shape. Okay, and this hinge is at 12 meters, which is this point here. Alright, so now we can draw the shape of the inference line. So the peak is somewhere here, right? So we just draw the inference line like this. Okay, now we have got the shape of the inference line, and we want to determine what is the peak value in the inference line there. Okay, so in this case we want to see what will happen, okay, when we put 1 unit force at a specific location. Okay, so this is the original beam with a pin here, and then with the roller support at B. Okay, so this is A, this is B, and this is D. Okay, so where is the point where we can conveniently determine what is the support reaction By, okay, when we place 1 unit force? Alright, so we want to see what happened to By, okay, which is the By here, and we want to select a point which is convenient for us to determine what is By. Okay, So naturally, if we place one unit force just exactly on support B, okay, so in this case, the support reaction here at A will be 0, okay, the support reaction at A will be 0, and then the support reaction at D will also be 0, okay, if you analyze for the reactions at A and D, you'll find that AY equals to 0, DY also equals to 0, and then BY is equals to 1 in this case, okay, due to this one unit force, okay. So in this particular case, we get By equals to 1. So meaning that if we place one unit force at 8 meters away from point A here, we are getting a value of 1 over here. Okay, so meaning that this point here, the value here is 1. Okay, so this corresponds to 1 here. Alright, and then now we want to determine what is the peak value here. So now we can use similar triangles. Okay, so we can use similar triangles like this, which is the yellow triangle. Okay, and then we can draw another similar triangle from here. Okay, so now we have two similar triangles, right? So now we have 1 over 8. We have 1 over 8 is equals to this value over 12. So in that case, we get this value as 1.5. Okay, so now we have got the inference line for BY. Alright, and then next, we want to determine the inference line for the moment at C. So the moment at C is at the midpoint between A and B. Okay, so now we draw the beam first. Okay, so at A we have a pin support, and then this is point C here. Okay, and B is a roller support. And then we have a hinge here, and then D we have another roller support. Alright, now at point C here, if we are interested in the bending moment, so in this case we replace point C as a hinge and then act upon the hinge with a pair of positive bending moment. Right? So in this case, this pair of bending moment will cause deflected shape like this. Okay, and then point B here, okay, point B cannot displace, it can only rotate. Okay, and then point D here cannot displace also, it can only rotate, and then this hinge here can also rotate. So the deflected shape will become like this. Okay, so now we know that the peak value will be at 4 meters, okay, and also at 12 meters. Okay, so at 4 meters and also at 12 meters. So now we draw the inference line shape first. Okay, so now we know that we have a peak here at 4 meter, and then another peak here at 12 meters, right? Okay, and then we have 0 at 8 meters, and then we have 0 again at 16 meters. Okay, so now we have a general shape of the bending moment at C, okay, for the inference line for moment at C. So now we want to know what is the peak value at 4 meters here, and also the peak negative value at 12 meters here. So in this case, we can start to do the analysis, okay, by selecting a point. So the best point for our analysis is point C, right? So now we have a beam like this, okay, and then the support at D, okay, and then we have another support at B, okay, and then we have a natural hinge over there. Okay, so to determine the peak value here, okay, so this is at 4 meters, so meaning that this is the bending moment at 4 meters when 1 unit force is placed at 4 meter. So this ordinate is the bending moment MC when 1 unit force is placed at 4 meter, right? So we put 1 unit force at 4 meter. Okay, so this is 4 meters away from support A. Alright, so in this case, we are going to get support reaction here is equals to 1 over 2, and then the support reaction at B here is also 1 over 2, and then support reaction at D is 0. Okay, so this is the reaction due to 1 unit force placed at C. Okay, so if we cut across a section here, okay, and isolate it as a free body diagram, okay, and then the 1 unit force is there, and then this is MC, okay, this is 1 unit force, this is 4 meter, right? Strictly speaking, there's still VC there, okay, but VC is not in the question here, so we just ignore VC. Okay, so from here you see that MC is equals to half times 4 meter, right? So in this case, MC is actually equals to 2, okay, and then the unit is meter, okay, but normally in the inference line diagram we don't put in the units, right? So meaning that the value of the ordinate here is 2. Okay, so meaning that the ordinate here is 2. Okay, so this is 2, right? Now we want to determine what is the key value over here. So in order to do that, we need to use similar triangles. So the first triangle that we look at will be the triangle here, okay, which I draw in yellow, okay, and then another triangle is the triangle that I draw in green, okay. So with these two similar triangles, okay, that is this yellow triangle and this green triangle, we can determine this value through these two similar triangles. Okay, so here we see that this base here is 4 meters. Okay, the base here is also 4 meters, right? And then the height here is 2. Okay, so since the base are the same, so this yellow triangle must be the same as this green triangle. Okay, so meaning that this ordinate here is also 2 but negative. Okay, so here we have negative 2. So with that, we have already drawn the inference line for the bending moment at C. Next, we want to draw the inference line for the shear at C. Alright, so we want to cut across section C here, okay, and see what is the inference line shape for VC. Alright, so for shear, we have to cut across the beam, okay, and then place roller guard at C. So this is point C. This is a hinge at A, and then this is the roller support at B, and this is another roller support at D, and then in the middle of B and D we have a natural hinge. So now at C, we want to act upon this roller guard with a pair of positive shear force VC. Okay. Okay, so once we act upon the roller guard with a pair of shear force VC, okay, then the structure will deflect in the dashed line manner, right? So this is the deflected shape of the beam when we apply a pair of shear forces VC, right? So now we want to draw the shear force inference line for VC. So at 4 meter here, we know that there's a jump of shear force like this, okay? And then from 0 to 4, we have negative shear force, okay? And then from 4 to 8 and to 12, okay, we have a line sloping down like this, okay? And then from 12 to 16, we have a shear force line sloping upward like this. So this is the general shape of the inference line for VC. Okay, but we still don't know what are the key values over here, here, and here. Alright, so now we want to select one point where we can determine one of the key values. Alright, so in this case, we know that one of the key values is at 4 meter. So meaning that we place 1 unit force at 4 meter here, okay, which is at point C, okay, and then we determine what is the reaction at point A there, and then what is the reaction at point B, and what is the reaction at point D, where we still have a natural hinge there, okay. So if we determine the reaction for this 1 unit force placed at 4 meters, okay, so this 1 unit force is placed at 4 meter. Alright. Then we have this support reaction, which is equals to half at A, and the support reaction at B is also half, and then we know that the support reaction at D will be equals to 0. Okay, so in this case, we want to determine what is the shear force at C, right? So now we want to see when the 1 unit force is just to the left of C. Okay, so when the shear force is just to the left of C, then we have a free body diagram like this. Okay, so the 1 unit force is there, and then the support reaction here is half, and then this distance is 4 meter, right? And then here we have shear force BC. Strictly speaking, we have moment MC there also, but we are not interested in MC, so we can leave it out. Okay, so in this case, if we analyze for VC, we will get VC is equals to minus half. Okay, so meaning that when the 1 unit force is just to the left of point C, the shear force at C is negative 1 over 2. Okay, and then when the 1 unit force have just moved to the right of point C, okay, so when the 1 unit force has just moved to the right of point C, then in our free body diagram, we don't have this 1 unit force anymore, okay, because this 1 unit force has moved to the right of point C. Alright, so we have VC here, okay, and we don't write MC there because we're not interested in that, and then we still have the reaction of half there, and this is 4 meter. Alright, so in this case, when we solve for VC, we are going to get VC is equals to positive of 1 over 2, okay, or half. So meaning that this value here is half. Alright, and then for the other key values, okay, we can make use of similar triangle that I have drawn in yellow, and then we use another similar triangle which is indicated in green. Okay, so in this case, both of these triangles are the same triangle, okay, because this is 4 meters, this is also 4 meters. Okay, so meaning that the value over here is also negative 1 over 2, right? So in this case, we have already determined all the key values in the inference line for shear at point C. Okay, so now we have solved all the 3 questions, which are the reaction at B, and then bending moment at C, and also the shear at C. Okay, so we have drawn 3 inference lines. Alright, so now we want to move on to another example in which we will see how are we going to apply the inference lines that we have drawn. Okay, so in this particular example, the beam is used to support a dead load of 0.8 kilonewton per meter. Okay, so dead load is applied throughout the span of the beam, right? Okay, so normally That load is not a moving load. Okay, so that load is applied across the whole beam, right? And then we have another live load of 4 kilonewton per meter length and a live load of 20 kilonewton point load. Okay, so live loads will be moving load, right? That load, static load that is applied across the whole member, right? And then live load can move, right? So we have a live load of 4 kilonewton per meter length and a point load of 20 kilonewton. So the first question is to determine the maximum positive reaction at B. The second question is determine the maximum positive moment at C. Alright? And then the third question is to determine the maximum negative shear at C. Okay? So now we can make use of the inference line we have drawn previously. Yeah? Okay? So let's look at the maximum positive reaction at B. Alright? So at B we have an inference line like this, which is the same as the inference line that we have drawn just now, okay, where the peak value is at 12 meter of 1.5. Alright, so now we have three loads here. Okay, so one is dead load of 0.8 kilonewton per meter length. Another load is 4 kilonewton per meter length live load, which is moving. And another load is the point load, which is 20 kilonewton. Right? So now we look at the first load of uniform load, which is the dead load. So dead load, as I mentioned, it is applied across the whole member, right? So this is the dead load, which is 0.8 kilonewton per meter length, right? And then for live load will be moving load. Okay, so first of all we look at the uniform moving load, okay, which is 4 kilonewton per meter length. Okay, so that live load, we place it also across the whole beam, okay, because now the inference line is all positive across the whole beam, right? So if we put the live load, which is the uniform load of 4 kilonewton per meter length across the whole beam, you will maximize the reaction at B. Alright, and then we have another live load, which is the point load. Okay, so point load, we can place it exactly at the maximum value of the inference line, which is 1.5, right? So we put the 20 kilonewton force at 12 meter in order to maximize the reaction at By. Okay, so the live load is 4 kilonewton per meter, which is the moving load, okay, for the live load. So in this case, alright, we have the effect of this 20 kilonewton force placed at 12 meters, and then we have a dead load, which is 0.8 kilonewton meter placed along the whole beam. Okay, so this does not change, right? Dead load has to be placed across the whole beam, right? And then live load we have a choice of placing across the whole beam or only part of the beams. But in this case, since the inference line is all positive along the whole length of the beam, so we place the live load along the whole span of the beam in order to maximize By. Okay, so the value of By due to this 20 kilonewton force is 20 times the ordinate of the inference line, right, which is 1.5, and then multiply by the force magnitude. Okay, and then the second effect is from the 4 kilonewton per meter length live load. Okay, so the effect of live load is the intensity of the live load multiplied by the area of the inference line. Okay, as we have learned previously. Okay, so the area of the inference line is the area of a triangle with the height multiplied by the base. Okay, so the base is 16 meters and then the height is 1.5 and then multiply by half. So this is the area of the inference line and then multiply by the intensity of the live load, we will get By. Okay, right? And also from the dead load, okay, it is the intensity multiplied by the area of the inference line. So in this case, the area is the same as this, okay, and then the intensity of the dead load is 0.8 kilonewton per meter length. So in this case, when we solve for this, we get 87.6 kilonewton, which is the maximum reaction at B. Okay. So next, we want to move on to solving the maximum positive moment at C. Okay. So now we use a inference line for MC, alright, for bending moment. So this is the inference line we have already drawn just now. So in this case, as I mentioned just now, the dead load has to be applied across the whole span. Okay, so we have a dead load where the intensity is 0.8 kilonewton per meter length. And now we want the maximum positive moment at C. So now we have a choice of placing the live load of 4 kilonewton per meter length on part of the beam only. Alright. So in this case, we are going to place the live load across the positive part of the inference line diagram only. Alright. Because now we want the maximum positive moment. Alright. So in this case, we place the live load only from 0 to 8 meter. Though this live load is with intensity of 4 kilonewton per meter length. Alright. And then don't forget we have another live load which is a point load. So for point load, we just place it at the positive side of the inference line where the ordinate is the maximum, which is 2 in this diagram here. So we place the 20 kilonewton point load at 4 meter. Okay. So therefore, the effect of this 20 kilonewton force on the bending moment at C is 20 times 2, which is the ordinate. Okay, so MC maximum for positive MC, okay, is 2 times 20 from this point load here. Okay, and then for live load, we only place from 0 to 8 meters, right? So in this case, it is the intensity of the live load multiplied by the area of this triangle here. Okay, the triangle from 0 to 8 meters, right? So the effect from the live load, okay, is this intensity multiplied by the area of this triangle. Okay, so the area of this triangle is this value here. Okay, and then this is the intensity of the live load, right? And then we have another effect from the dead load. So dead load, as I mentioned, is not a moving load. Okay, it is always placed along the whole structure. Okay, so the effect of dead load is the intensity multiplied by the positive area plus the effect from the negative area as well. Okay, so we have a positive area multiplied by 0.8. Okay, and then we have a negative area from the inference line multiplied by the intensity again. Okay, so from here the solution is 72 kilonewton meter, which is the maximum positive shear at section C, okay, with this loading. Alright, so now we want to look at what is the maximum negative shear at point C due to these loads. Okay, so this is the inference line for shear at section C that we have drawn just now. Okay, so now I want to see how I'm going to place the loads. Okay, so first of all we look at the dead load. So dead load, as I mentioned just now, it has to be placed along the whole beam. Okay, because it's not a moving load. So this is a dead load of intensity 0.8 kilonewton per meter length. Right? And then secondly, we want to look at the effect of the 4 kilonewton per meter length live load. So live load, we can place them partially on the beam. Okay, so now we look at where are the locations of the negative inference line for VC. So we have from 4 meter to 0 meter or 0 meter to 4 meter. So we can place the 4 kilonewton per meter length force there. And also we have negative values from 8 to 16 meters. So we can place the uniform load of live load of 4 kilonewton per meter length from 8 to 16 meters as well. Okay, so these are the live load, okay, with intensity of 4 kilonewton per meter length, and is placed from 0 to 4 meters and from 8 to 16 meters. And then lastly, we want to look at what is the effect of the 20 kilonewton point load. Okay, so we have one negative value at 4 meters, which is negative 0.5. We have also another maximum negative value at minus 0.5 also at 12 meters. Okay, so meaning that wherever you place the 20 kilonewton force, the effect will be the same. Okay, you can either place it at 4 meters, okay, or you can either place it at the 12 meter. Alright, so in this case I'm going to place at 12 meter here. Okay, so my 20 kilonewton point force is placed there. Okay, now we want to determine what is the maximum negative shear force at C. Okay, so first we look at the effect of the 20 kilonewton force. So the effect will be 20 kilonewton multiplied by negative 0.5. Okay, and then secondly, we want to look at the effect from the 4 kilonewton per meter live load. So this 4 kilonewton per meter live load is placed from 0 to 4 meter and also from 8 to 16 meters. So now we want to look at the effect of the live load of 4 kilonewton per meter length. So this load is placed from 0 to 4 meters and from 8 to 16 meters. Alright. So the shear force is given by the intensity of this force multiplied by this area from 0 to 4 meters, okay, which is given by this expression here, okay, which is a negative value, okay, and then we have the effect for this part of the uniform force of 4 kilonewton per meter length as well, okay, which is the intensity multiplied by the area here, which is the negative area. Okay, so the negative area is here, and then the intensity is 4 kilonewton per meter length, right? And then next we want to look at the effect of the dead load. So the dead load is placed along the whole beam, right? So now we have 0 to 4 meters, okay, which is a negative area, okay, and then we have from 4 to 8 meters where the area is positive, okay, and then we have from 8 to 16 meters where the area is negative, right? So if we sum all these effects here, we are getting negative 23.6 kilonewton. So this is actually the maximum negative shear force at sea with arrangement of loads like this. Okay, so that's all for this tutorial solution. Thank you very much for watching.